C18, carbon 3, cis 9, 12, and 15. So how many isomers going to generate? 6, is that right? Yeah. If it's linolenic acids, this is a linoleic acids. If it's a linolenic acids, it's going to have 6 isomers. Oh, okay? So that's why I wanted to tell you, at the end of the day, it's a messed up of everything. If you have some food products, for example, you have a meat, you have a microbe in there, even you vacuum package, you expose to the light, become a single-letter oxygen. If it's like a grass-fed beef, you have a linolenic acids there. 6 different types of isomers and 6 hydrogen peroxide are going to generate. And at the end of the day, it's followed with everything. So when it smells really bad, when it's oxidized. That's the reason. And if in the room temperature, you put it there like a very hot 35 degrees Celsius, 32 degrees Celsius, put it in the lab, you didn't take care of the trash, in the second day, it's awful. That's the reason. That's the reason that if I show you that, that's lots of isomers will be generated because of the chain migration. Okay? So that is an example for linolenic acids. Now, last example I also want to mention. We talk about the lipids oxidation, very difficult to avoid it. Because in some of the products, there is an enzyme for that. So I'm going to take this whole thing out. The enzyme which is responsible for the lipids oxidation. So what is that? That's called the lipoxygenase. It is an enzyme. We're using LOX as an example, as an acronym. Lipoxygenase is an enzyme widely existing in soybean and pea, those products. That's why the soybean and the pea, the sunflower or the soybean oil, you will feeling beanie later on if it storage too long. Now, the lipoxygenase, LOX, it usually containing a special stuff called Fe2+, which is ferrous iron. This is a non-heming ferrous iron. Now, for this special enzyme, they organize a special structure which is exactly right here in the linolenic acids is 1,4-pentadiene. Okay, so this is what it looks like. Now again, it's 9, 10, 11, 12, and 13, 14, and this is 8. This is called 1,4-pentadiene. Because this guy can recognize here. Now, how they recognize it? How the reaction gonna become? We can do some of the. We can draw the picture right here. They're gonna attacking the carbon number 11. The carbon number 11, the structure we call it a conjugated double bonds. These two here, we call it conjugated double bonds. And I would mention that once you have a conjugated double bonds, the energy for the reaction is low down to 79. Continue to roll down. So what happened? Usually here, it will generate a free radical coupled with LOX with Fe2+. Okay, once this free radical comes out, what's going to happen? Eight, 9, 10, 11, 12, 13, and 14. once this free radical comes out, it goes here. I'll draw like that. LOX at Fe2. This migration, this chain happened, the migration goes here. So here we'll actually have O comes out. It goes right there. Alkoxy radical goes to the carbon number 3. Okay, then we're going to have that. Once this happens, this is Fe2 plus. The Fe2 plus will become Fe3 plus, which means from the ferrous status become a ferric status. Once you become a ferric status, what that means? You donate 1 electron. So when you donate 1 electron, where they go? They attach to this free radical there, alkoxy radical there. Therefore, this become a minus. Okay, they become a minus. Once they become a minus, you know that in the system, you have started to have a fatty acids reaction. What's going to generate? What is dominating? This guy. Is that right? Proton, hydrogen ions will be everywhere. These hydrogen ions can't go there. So finally it becomes what? Hydrogen peroxide become. So this is like hydrogen peroxide, hydrogen linoleic acids. Now, once this hydrogen peroxide goes there, Fe3 solved the problem. So they finish their job. They're going to return it back to the ferrous status. And then these two will be released, so they become a separate, which is a lipo-oxygenases and Fe3, they are separate. Fe2 plus, they're separate. And then they go to find another pentadiene, continue to do the reaction. So this is what I tell you one thing is that the special structure of some of the fatty acids, they also going to be contribute to the progress of the lipids oxidation. When you have a 1,4-pentadiene structure, it's very easy to recognize by the lipo-oxygenases. So it will be speed up the reaction. Okay? Those enzymes we also call it a pro-oxidant. PRO, pro-oxidant. Now the last one we want to briefly mention about antioxidants. What are they? How does it work? We have a slide we're going to talk on Thursday. Antioxidants, there is a natural one, which is called alpha tocopherol.
Vitamin E.
Yeah, with the heat.
No, E. Isn't that E? Vitamin E.
Or EL, ferrol. Yes. So, how they reacted? You have an AR. You have an AH, sorry. You have an AH. And then you have a free radical. So what they reacted becomes a HR, and this A gonna release. Okay, if you have AH working with ROO, which is a perioxy radical, what's gonna happen? It's gonna become a ROOH, which is hydrogen peroxide, and then they release a radical. However, there is something you need to know. Biochemistry reaction, organic chemistry reaction, most of them are reversible. So, this concentration we usually do is 50 to 100 parts per million ppm. You can be higher than that. If it's too high, what's going to happen? This goes back, this goes back. free radical re-release and free radical re-release. And you lose the function of the antioxidants. Actually, you promote the oxidation because they release it. So that's why some of the people want to eat some vitamin C, vitamin E, or like lycopene, or those type of the commercial products. You have to follow the instruction. You can't eat too much. Once you eat too much, the free radical will be released, come back, because that's a reverse reaction. Okay? So, this is almost, I get it down. The last thing I want to mention, they have a research already done for stearic acids, oleic acids, linoleic acid, and the linolenic acids for their possible speeding and the ratio for happen, how possibility, how fast it will happen for the lipids oxidation. If stearic acid is 1, then the ratio will be, compared to oleic acid is 100 times easier to have lipids oxidation compared to stearic acids, because 1 double bond. How about linolenic acids? 2 double bonds, it's going to become 1,200 times more than stearic acids. How about linolenic acids? Because 3 double bonds, it's 24,000. Close to 25,000. 24 to 25,000. So you can see, you have a 3 double bonds there, unsaturated fatty acids compared to stearic acids. How fast it is? It's 2,500 times easier to have lipids oxidation. This is the problem for these type of products. So therefore, what we do? Hydrogenation, they do it, is that right? They put them back. And then they make the products like margarine and shortening, all those stuff. Because they try to prevent the rancidity. And you can have a longer shelf life, it's for the food security. However, those things are not easily to be digested by the body, so therefore you have those all kinds of cardiovascular disease comes out. So that is a contradiction between these things. When we talk about lipids oxidation, we talk about is a lipid reaction, but when we talk about the other things, is talk about the health. Okay? So that's, I think all I have today is for, the introduction of the lipids oxidation. Okay? So Thursday we'll talk about the slides.